Okay, today we're going to learn about logarithmic functions and their properties. This is our new unit. We're going to talk about logarithm functions. They were invented to deal with large numbers or very small numbers. So you'll use this a lot in any fields that involves large numbers and small numbers. For example, microbiology, you'll use a lot of logarithms. Also astronomy, when you're talking about distance between planets, definitely going to be used logarithms and stuff like that. You'll also see it used in other fields, such as calculus and some physics and stuff like that you'll see it applied. But basically, these are the skills that we're going to be looking at today. So by the end of this video, you should be able to recognize and evaluate logarithm functions with base A, write exponential equations in logarithmic form and vice versa. So we've got to convert between logarithm and exponential form. Use the properties of logarithms to evaluate and rewrite logarithm expressions. Then apply those properties to expand or condense logarithm expressions. And then we're going to end with something called the change of base formula to rewrite exponential and logarithm equations. So what is a logarithm? A logarithm function with base A is an inverse function of the exponential function y equals a to the x. Okay, so basically, remember our inverse functions are where you switch your x's and y's. So that's what we're going to do here, but it's a little bit different when solving for the x when you switch it. So our official definition of a logarithm is for x greater than 0, a greater than 0, a cannot equal 1, y is equal to log base a of x, if and only if x is equal to a to the y. That's where the a and the y, the x and the y switch, your domain and your range of switches. The function f of x equals log base a of x is called the logarithmic function with base a. So notice that the subscript I read as base. Log base a of x. All right, so first thing we want to do is we're going to learn how to convert in between logarithm and exponential form by switching our x's and y's. So we're going to look at example A here. We have log base 4 of 16 is equal to 2. And we want to convert this into exponential form. So remember, from our definition up here that I just highlighted, our switch, notice where the y's and the x's are. So my base becomes the base of my exponential. What it was equal to becomes my new exponent. And what was inside the logarithm is what my function is now equal to. So 4 squared equals 16. And here it'd be 64 to the 1/2 equals 8. So that's how you switch. You should have got base 9 to the negative 1/2 power is equal to 1 over 81. Okay, let's go in the other direction now. I'm going to give you the exponential equation. I want you to convert it into logarithm. Remember, the base stays the base. So this becomes log base 5 of 125 is equal to 3. So our x's and y's switch. Okay, b, same thing. Our base is going to stay as the 9. All right, so notice that the base 5 of the exponential is the base of the logarithm. And then we switch our x's and y's. So what was outside, what our function was equal to, which was 125, is now inside our logarithm of 125. And what was outside, the exponent of 3 is now, what was our exponent inside the cubic operation is now outside. So log base 9 of 27 is equal to 3/2. Okay, you try this last one. Convert this exponential into logarithm form. That becomes log base 24 of 1 equals 0. When evaluating logarithms, remember that a logarithm is an exponent. This means that log base a of x is the exponent to which a must be raised to obtain x. So they just remember they work back and forth. So mathematically statement, that is log base a of x equals y, then a to the y equals x. So it's just saying that by definition is the relationship, or definition of logarithm is defined by its relationship with the exponential function. Okay, so we're going to evaluate each of these logarithms. So we don't know how to work with logarithms yet, so we're going to evaluate these by converting them into exponential form. So first thing I do is say, okay, this is equal to y. So if I switch that, it becomes 4 to the y is equal to 16. And then rewrite 16 as 4 squared. And then you can do the 1-to-1 property. If you have the same base, you can just set your exponents equal. So the only way y to the 4th can equal y squared is if y is actually 2 as well. So you try this one. So switch it to exponential form. Rewrite 125 as 5 cubed. And then say y is equal to 3 using your 1-to-1 property. I went ahead and rewrote this as log base 4 equals 16 log base 4 16 is equal to 2, and log base 5 at 125 is equal to 3 because I asked you to evaluate. So you want to We didn't ask to solve for y. Okay, we're going to do the same thing here. I'm going to evaluate this function at x equals 1 over 81. So basically, it just becomes log base 3 of 1 over 81. And so remember, I can make that equal to y, and I can rewrite my logarithm as an exponential. So that'd be 3 to the y is equal to 1 over 81. And then remember, 81 is 3 to the 4th, so that'd be 1 over 3 to the 4th. And then anytime you have an exponent in the bottom, you want to move it to the top of a fraction, you just make it change the exponent to a negative. So that becomes 3 to the y is equal to 3 to the negative 4. So y must be negative 4 by the one-to-one property. So therefore, I can conclude that log base 3 of x, or log base 3 of 1 over 81, must be negative 4. Okay, you figure out this last one? I can rewrite this as log base 2 of 1 over 8 is equal to y, and then 2 to the y is equal to 1 over 8. 8 can be rewritten as 2 to the 4th power, or cube power, sorry, and then 2 to the y is equal to the negative 3rd power, and so y is equal to negative 3. So my conclusion is log base 2 of 1/8 is equal to negative 3. Now we've been doing log base a, so log base 2, log base 4, log base 25, whatever it happens to be. There are a couple logarithms that occur quite often in nature, and they have their own notation. And that is, the first one is called, when the base is 10, log base 10, is called the common logarithm function. And we just write log with no little subscript because it's so common that it occurs. The other one that occurs quite often in nature is when the base is e. This is called the natural logarithm, logarithm naturel, which we abbreviate as ln. Now let's talk about the properties of logarithms. There's quite a few, so I'm going to break them up into a couple of sections. The first logarithm property we're going to learn is when you have the logarithm of any base that's a log base of a of 1, when 1 is inside the logarithm. Regardless of what base that is, what a is, log base a of 1 is always equal to 0. And the reason for this, if I convert that to exponential form, I have a to the 0, and we know anything raised to the 0 power is 1, so we're using our rules of exponential. So if I'm doing a natural log, remember natural log has base e, so the natural log of 1 is also equal to 0. Log base a of a is equal to 1 because a to the 1st power is equal to a. And so natural log of e is also equal to 1 because that would be converted to e to the 1 is equal to e, which is true. So those are a couple of properties you need to memorize. Now the next one is if we have log base a of x equal to log base a of y. Two logarithms of the same base can only equal if and only if what's inside the logarithms are equal. So that would be x must be equal to y. That converts to our common log and our natural log. So this is called the one-to-one property of logarithms. And if we have log base a of a to the x, the exponent and the logarithm kind of cancel each other out, and you're left with just the x term. And that is true if I have a raised to the log base a of x is also equal to x. And that's basically from our inverse property of f of the inverse of f of x. When you did that compound function, you got equal to x. Well, we're doing the same thing here with logarithms and exponential, and so that's called the inverse property. All right. There are a couple ways that we're going to use these properties. The first one here is going to evaluate logarithms. So we have log base 2 of 16. And so I can rewrite 16 as 2 to the 4th. So I have log base 2 of 2 to the 4th. Remember, log base 2 and the 2 exponential cancel each other out. And that leaves us with the x as our answer. So I'm using this inverse property for this example here to get 4. Okay, next for b, log base 2 of 1. Remember, doesn't matter what base it is. Anything where it's 1 on the inside, that logarithm is equal to 0. All right, I want you to try log base 3 of 81. First thing I'm going to do is I'm going to rewrite 81 as 3 to the 4th power because I'm going to get the same base. Then I'm going to use that inverse property and write it as 4. Okay, now I'm using the inverse property of c and rewriting that as 13. So that notice that our last example and c have the same property. Now for this d, we're going to do the one-to-one property and set what's inside the logarithm equal to each other and just solve the equation for x. And I get x is equal to 7. So you try the last one. Using the one-to-one property, I can take what's inside the natural log and set it equal to what's inside the natural log, and then solve for my x. I end up that x must be 3. Okay, now remember I said there was a lot of properties of logarithms. Now we're going to continue to learn the properties. Our product property says if I have log base a of u times v, so a function times another function, that is equal to log base a of the first function plus log base a of the second function. This is how we expand out the logarithms. Now this computes to our natural log as well as our common log notation. I chose to use the natural log notation, a log base u plus the log base v, a log of v. natural log of u plus natural log of v. Our quotient rule, when we are dividing inside a logarithm, we break it up by subtracting. So we have the natural log of u minus the natural log of v. Our power property is kind of cool. If you have log base a of u to the n, so this time notice that my base u is not the same as the base of the logarithm, so I can't use the inverse property. So when you have this, you just bring the power to the front and multiply by it. So the natural log of u to the n becomes n to the natural log of u times the natural log of u. Now we're going to use this in quite a few different ways. So our first technique is going to be like example 5. Where I give you the logarithm value of a certain common log. So I'm using the common log notation here. So the common log of 3 is equal to 0.4771, the common log of 4 is 0.6021, and the common log of 5 is 0.6990. And we're going to use these properties to evaluate this. So log base 12, I can rewrite 12 as 3 times 4. So that means that's log of 3 plus log of 4. And then I can plug in my given information, and all I have to do is add these two together. And we get our answer of 1.0792 when I round to 4 decimal places. So I want you to figure out log base 50 without using your calculator. Just use the given information. So I can rewrite 50 as 10 times 5. So that's log of 10 plus the common log of 5. Now, this one's a little bit harder to see because I gave you the log base 5, but I didn't give you log of 10. But remember, the common log understands that the base is 10. So when you see log of 10, that's actually understood to be log base 10 of 10. And remember, when you have a log base to the same power, we had that property here at the very beginning that is equal to 1. Log base a of a is 1. So that means I can replace this common log of 10 with 1. So that becomes 1 plus 0.6990, which is 1.6990. All right, continuing on. We see the exact same property here on the first one. We have the log base 12 of 12. Well, that's same base and side, so it becomes 1. And log base 2 of 2, that's 1 again. And log base 9 of 0 or 1 is 0. Remember, anytime there's a 1 inside 0. So my answer to this equation is 2. And that's using our properties that we learned earlier. So now I want you to try to use your quotient property or your product property to figure out this one. Log base 15 minus log of 15 minus log of 4. Log of 15 can be rewritten as log of 3 times 5. And I get log of 3 times 5 minus log of 4. And then log of 3 times 5 is the same as log of 3 plus log of 5 minus log of 4. And then I can just substitute in my given information that was given to me. It was given that log base 3 is equal to 0.4771. Log base 5 we know to be 0.6990. And log base 4, common log of 4 is 0.6021. Adding and subtracting those to get our answer of 0.574. All right, now I said there was a number of different ways that we're to use these properties. So another technique that you'll be asked to do is condense your logarithms. You'll need this when we have to solve logarithm equations later on. And to condense a logarithm, that just means we're going to combine these using our properties until we get a single logarithm. Now we can only condense logarithms that have the same base. So notice in A, both of our logarithms are base 5. So we can condense these by using our properties. So remember, if I'm adding two logarithms together, I condense them inside to become multiplication. So that becomes log base 5 of just 12. And that would be my answer. You condense until you get a single expression. Now here we have a couple properties. We have an exponent moved to the front, and then we have adding and subtracting. Order of operations says we need to deal with exponents before we do a multiplication and division. So I'm going to move the exponents into the logarithm, as I just did here. Now I'm noticing that I'm adding two logarithms together, so that means I'm going to multiply 9 to the 1, r to the 1/2 times the 5 to the 1/3, and I'm subtracting t to the 1/5, so that means inside the logarithm I will divide by t to the 1/4. Okay, for this example, notice that we all have the same base. These are all common logs, so the base is 10. So I'm going to start by doing my addition and my subtraction. And remember, when I do addition, that becomes multiplication. So that this will be log base 1 times 10 minus common log of 0.1. And then that is 10 divided by 0.1. And then 10 divided by 0.1 is 100. And then remember, the common log is base 10, so I could rewrite this as log of 10 squared, because 100 is 10 squared. And remember, the 10 to 10 cancel out, and we get our exponent of 2. And so our answer is just 2. Okay, you try this next your turn one. So start by moving your exponents in. So that becomes 16 to the 6th and minus log base 4 of 4 cubed. All right, now the 16 I notice can be written with base 4. So I'm going to rewrite that as log base 4 of 4 squared, and that's going to be raised to the 6th power. Log base 4 of 4 cubed. Now remember, when you have a power of a power, you multiply them together. So I can rewrite this as log base 4 of 4 to the 12th power minus log base 4 of 4 to the 4 cubed. And then remember our power of a power rule, our logarithms rule here, that just becomes 12 minus 3, which is 9. Whew, let's try this next one with see how you do on it with all these parentheses. Okay, order of operations say we need to deal with what's inside the parentheses first. So I'm going to combine those by first taking my exponent, my 2, and moving it into my logarithm and making it a exponent, a squared power. Then inside the logarithm, inside the parentheses again, I am multiplying 2 logarithms together the same base, so I can put that together and multiply their inside functions. And now I'm going to deal with my power rule. So I'm going to take everything that's inside my new log base 4, and I'm going to raise it to the 1/2 power. And then here I'm going to move that. All right, so I have x plus 1 to the 1/2 power times by x minus 1, and then squared to the 1/2 power just becomes the first power. Next, I'm going to deal with that 6 outside of the log base 4 of x in the last term. I can fix that by moving it to the inside, making it x to the 6th. Now I'm finally ready to deal with this addition, which makes it multiplication. So my final answer is going to be log base 4 of x plus 1 to the 1/2 times x minus 1 times x to the 6th, all inside that logarithm. Okay, we're going to expand each of these logarithms. So with expanding, we're going to do the opposite direction. We have a single logarithm, we're going to make it out to multiple logarithm terms. So again, we're going to do order of operations, but this time we're going to start with multiplication division in this case. So division tells us I can break this up to log base 3 of 2x minus log base 3 of y, but I'm not done because inside this first term, I got 2 times x. So that becomes log base 3 of 2 plus log base 3 of x minus log base 3 of y. Whew, finally done. Now for B example, because of the parentheses, I have to deal with that exponent first, so I need to bring it out to the front, and then I'm going to divide up my logarithm, but notice everything inside that parentheses needs to be squared. So I have to remember to put this in parentheses, and then I can distribute the 2 to each of my logarithm terms, because our final answer, we don't want any parentheses at all. And so that'll be my answer. Now there's another way that you can approach this problem. Whichever way makes more sense to you, you can. I can first distribute that square to the numerator and denominator inside my logarithm. Then I can break up my fraction by the division and make it subtraction. Then I can do my power rule and bring the power to the front of each of those terms. And I get the same answer as I did the other way. But this way I didn't have to remember to put in parentheses. Whichever way makes more sense to you. Okay, for C, I'm going to start by breaking this up. So I have log of 5x plus common log of y to the 4th plus common log of z to the 7th. Then I'm going to use my power rule and bring the powers to the front. And you are done. Okay, you try the next one. We're going to start with our quotient rule. Then we're going to use our product rule and make it addition. Now I got to put parentheses because all of this is division. So I'm going to do my product rule here, but notice it's inside the parentheses. Then I'm going to deal with my exponents. And here I'm going to distribute that negative to each of the terms, making this this last term minus 3 natural log of z for my final answer. All right, so this one, first thing I got to do is remember a square root is the same as something raised to the 1/2 power, so I need to rewrite that. Because the power is on the outside, I'm going to take it to the front first. And then now inside the brackets, I'm going to use my quotient rule. And then inside the brackets in that first term, I'm going to use my product rule and break it up. And then my last step, I'm going to distribute that 1/2 to every one of my log terms to get rid of my parentheses and have my final expanded form. Okay, let's see how you did on this one. So first I'm going to rewrite that fifth root as to the 1/5 power. Okay. Bring that 1/5 to the outside. Then I'm going to use my product rule. And then for the first term, I'm going to use my power. I'm going to distribute the 1/5 to each of the terms. And then I'm not quite done because I still have an exponent in that first logarithm term, so I need to bring it out. And 2 times 1/5 is 2/5. And now you completely expanded out this form. I cannot break out that x plus 2 because I don't have a rule about that. All right, last thing we're going to learn is something called the change of base formula. This was used mainly before we had calculators and, well, really complex calculators. It's where most calculators, basic calculators, can only use the common log or the natural log. And so if I want to convert log base a of x using just the common log or the natural log or to any log base, it's going to be log base b of x over log base b of a. So basically the key is, it doesn't matter what log base you do, the key is that the base of the original function goes into the base of the fraction when we do the change of base formula. So the common log of a to the x is equal to log of x divided by log of a. If I want to use the natural log to rewrite log base a of x, that's going to be the natural log of x divided by the natural log of a, because the base goes into the basement. And then I'll punch that into my calculator. So to evaluate log base 4 of 25, I would write that as common log of 25 divided by the common log of 4. And then I would use the log button calculator, which is found next to the 7 on your TI, and type this log 25 divided by log 4. Now here I'm going to use the natural log, but I'm going to do the same thing. Natural log of 12 divided by natural log of 2 gives us 3.5850. Pause and see if you do the common log and see if you get the same answer. You should. It doesn't matter which one you use. All right, and for this one that you tried, I'm going to use the natural log. So natural log of 22 divided by natural log of 5 is equal to 1.9206. If you use the common log, you got the exact same answer, so it does not matter which one you do. Okay, and so that is our introduction to logarithms.